Now that we understand the floating point representation in the computing system, let's also look at and understand floating point challenges, and especially in the programming concept. Let's talk about first thing, underflow error. Okay, underflow, like as I mentioned in overflow discussion of subtraction addition in that area, as I mentioned that underflow is not an overflow of subtraction. Like some people thinks that way. Okay, your addition gives overflow because it cannot represent and it's a too huge value to be represented, so that's overflow. Similarly, with the subtraction operation, you get to too small value and that becomes underflow. No, both of that case is overflow. But underflow is related to the floating point. Okay, it's an error if the result is too small to be represented by the format. As we have seen that you can represent pretty small number, okay, but even in our real life problems, that mathematics crunching, we could come across certain situations, certain result which cannot be, it is so small that it cannot be represented even with this number of 32 bits, with the exponent and fraction bit patterns. We cannot represent that, and that becomes an underflow error. Now, to avoid the frequent underflow error, a double precision, which is a double type in C and Java format, has been recommended in IEEE 754. So in this case, you have 64-bit pattern where MSB is sign bit, of course, but exponent is 11-bit and 52 is a fraction bit. Of course, you still have an underflow error, but which probably least likely to occur frequently. It is least likely to occur in most of the scientific computations. So it works so far, 64-bit, no problem. Of course, like in more precise calculations, like very like you are actually computing trajectory of your rocket launching and stuff like that, you might want to go with the 128-bit arithmetic. Okay, so it's basically can be extended similarly. It's all matter of how you're handling at your software level all these bit patterns. So anyway, with the 64-bit exponent representation, smallest magnitude is almost 2 to the power e 10 to the minus 308, and highest magnitude is 2 into 10 to the power 308. Okay, so this is quite a big range, and we can represent quite a small amount there. 64-bit so far works good, most of the cases. Now, second problem is a rounding error. Okay, so what we are trying to do here, we are trying to packet infinite number of real numbers within finite bit pattern. This will always raise to approximation of certain extent, right? A value, for example, even in the arithmetic world, 7 by divided by 3 is 2.3333, it's recurring, right? Cannot be represented by any finite bit pattern of the floating point number. You take it 32-bit, 64-bit, 128-bit, or any number of bit. You cannot represent 7 by 3. It has always been approximation towards this 2.33333. The nearest representation, another example, in 0.10, which is pretty like uniform number, right? 0.1. In a 24-bit system, you cannot represent it. It basically it's kind of 0.09999 some values, which is off by very little, like this much. But in a real system, that actually can, if this rounding error is accumulated over time, it can deviate your result from the target, and which was observed in case of this Patriot missile failure to intercept the Scud missile during Gulf War 1901 and causing death of 28 soldiers, right? After 100 hours of operations of that monitoring system, accumulation is so much that it caused like 0.34 second off from the calculation from the target, which caused a havoc. So this is a real life implication that you need to understand when you are programming, and we need to take care of this rounding error, and we need to it called a result tuning. So if you know your algorithm can accumulate errors, you basically time to time within certain frequency interval you tune up your value so that you offset from this accumulation of the rounding errors. And another small thing is now we have -0, +0. Of course, in the software world, we don't handle with that. Digital circuit must take care of this signed zero operation. That's another challenge, but it's mostly on the hardware side. Another practical problem, equality test of the floating point may not be reliable. Like if there are two floating point variable like float and float B, and you are trying to test equality of them, equals is not recommended, because it might happen this float A and float B are coming from various different floating point operations, and by your algorithm they're supposed to be same and some with some conditions, but that exact bit level representation may vary from one another, because remember they are all approximation of some representation, and there are rounding errors can accumulate around that. Though you print, basically if you do a cout of this float A float B, they will print the same value. Okay, why? Because this printing also round up representation, okay, and print certain values. Now if you actually increase the precision of the printing only at that, with that approach you can actually see the variation of the value between these two numbers. Normal, with the normal precision of the cout, you will see it's printing same value, but you will observe that this equality is not holding even if your cout is printing the same value for float A float B. Means you expect this block of code to be executed, it is not executing, it is going in a else part of that conditional block. Now to do that, it's always recommended is to have a this way. You compute the difference of float and float B, make it an absolute value, so it's kind of an del or difference. It is basically absolute difference between two values, and you check if it is smaller than some threshold like 1 e to the power 10 or 1 e to the power 12, depending on what application program you are writing, what's the target application, and what's precision you are looking for in the calculation. You check less than with a very small threshold value. So you take a difference, make an absolute difference, and compare that absolute difference with a very small threshold value. And if they are smaller to that, you assume they are equal.